After studying this module, you will be able to know or state the characteristics of a group. Verify the characteristics of the group through common examples. Know the total symmetry operations generated by a symmetry element. Also know the symmetry operation generated by all elements of the molecule. It is the symmetry operation that constitutes the group and not the symmetry elements. See the effect of symmetry operations on water molecules and equilateral triangle. Define subgroup into the main group. Find subgroups in the main group. Example of the main groups and subgroups in it. Know what is similarity transformation. Characteristics of conjugate elements. How to find a class in a group. Subgroups in water molecules and pH3 molecular point group. Some simple rules for finding a class in a group. After studying this model, you shall be able to define a group, know or state the characteristics or conditions or postulates of a group, verify the group postulates through number of common examples to understand the reciprocal theorem and know about some other common types of group. Now, in this module, in order to utilize the molecular symmetry of molecules for solving problems connected with molecular structure, bonding and spectroscopy, it is necessary to link the symmetry properties through group theory to various properties of the molecule. Molecular symmetry together with group theory can be used in number of applications such as simplification of quantum mechanical equation, explaining hybridization theory, chemical reaction theory, finding wave functions, spectroscopy, John-Tauler theorem, catalytic theory, theoretical prediction of molecular geometry, dipole moment, optical activity, ligand field theory, and many other chemical applications. Even we can predict the optical activity as well as dipole moment of the molecule. Cataloging the molecules symmetry wise is vital and very important. Symmetry of the molecule reveals many properties of the molecule. That is, either the molecule is ABA or it is AAB if I take a bent molecules. And these can be easily verified or identified with the help of the molecular symmetry and group theory. The important aspect of the symmetry of water and CF to Cl2 are same, but they are quite different molecular species. This is not clear without the help of the group theory. Therefore, one should have some basic knowledge of mathematical group theory in order to deal with this subject in connection with molecular symmetry. Group theory began as a branch of pure mathematics dealing with pure numbers only. Group theory is the mathematics of symmetry. Historical development of group theory has three basic roots, and these are theory of algebraic equations, number theory, and geometry theory. Discussion of all these roots is not, I will not be able to explain in these small modules, but it is necessary that how this theory was developed. In order to prove that there is no general algebraic solution for the roots of quantic equation or any general polynomial equation of degree greater than 4, group theory was developed independently through the efforts of Abel and Galois in the beginning of 19th century. In this module, basics of group theory as relevant to the discussion of the molecular symmetry will be discussed only. No other attempt will remain. Now let us say how to define a point group. According to the formal definition of a group is a set, or you can say collection of numbers which are combined with certain operations, such that group contains an identity element, group contains inverse, the group operations are associative, and group is closure under all operations. In mathematical sense, a group may be defined as a collection or set of elements or numbers having certain properties in common. That is, these elements are bound by certain conditions known as group properties or group postulates. The elements do not need to have some physical significance. Now, in these modules or in molecular symmetry, my emphasis will be mainly on symmetry operations as the collection of elements into the group. Now, the four basic properties of the groups. These four basic properties of the group must be strictly adhered by the elements of the group if they belong in truly to the group. Now, in order to explain these four basic conditions, let us take the group elements as A, B, C, D, E and X, and the four conditions can be stated in this manner. That is, condition 1, in this collection of elements, there is one element always that must be present. That is, when this element is combined with other element, that element is not changed. That is identity element. E, when combined with other elements will not be changed. Say A multiply E or combined E gives A, B combined with E gives B, C combined with E gives C, so on. Even if they take the other combination, E combined with A or E combined with A, I get the same result. That is, here combination of elements with E is commutative in nature. Otherwise, in group theory, this element combination may or may not be commutative in nature. Now, every element in the group must have its inverse. That is, say if I take X, which is a member of the group, then A into X and is equal to X into A is equal to E. Here I mean to say that each and every element has its inverse. If A is the element, let X is its inverse. A combined with X, that is A combined with its inverse, gives me the identity element. This is true for each and every element, that is element combined with its inverse gives me identity elements. Inverses are unique in nature. That is, there exists only one identity for every single element, so these are unique. Now, although the combination of two or more elements may not be commutative, but it must be associative in nature. That is, if I take the product A within bracket B C, it must be equal to AB within bracket into C, that is equal to ABC. Here the condition is the order of combination should not be disturbed. Then and only then this associative law of this combination will be there. The fourth condition, that is the closure, result of combination, that is in mathematical sense multiplication, addition, subtraction, or in symmetry sense one symmetry operation followed by another symmetry operations, or I can take the combination either of the same element or number of other elements. The net result which I will get, another element, and that another element should also be the part of the group. That is, all type of products or combination ultimately should result the element which belongs to the group. In a group which I have defined earlier, A, B, C, D, X, these types of combination and their results must be AB is equal to C, AC is equal to D, BC is equal to another element of the group. It is not there necessary that the combination AB is equal to combination BA. That is, these types of combination may be commutative or non-commutative. Order of combination matters a lot in a group. This order of combination is very significant. This is true in the case of product of symmetry operations when carried out. So, we must very careful to preserve the order of combination. Now, let us take some example to verify the characteristic of the group. Let me take the first example and show that a group which contains only 0 as the element, does it belong or does it make a group? Yes, if I say let us take a group with 0 as the element and mode of combination as addition constitutes a group. Group contains only single element 0 in it. Property number 1, that there should be an element into the group such that when it combines with each and every element of the group, it leaves it unchanged. Now, since the group contains only 0 as the element, such elements be 0 itself. That is, 0 is also the identity. If I add 0 plus 0, I will get 0. So, element 0 is unchanged. Property second, each an element must have its inverse. Here, inverse of 0 is itself 0. So, like this, you can verify all the 4 properties in this group. So, we can say 0 group, that is a group which contains 0 as the element with mode of combination as addition constitutes a group. Now, let us take simple example of the elements, all negative elements and all positive numbers. We take all integers, negative integers and positive integers, and the mode of combination as addition and 0 as the identity element. And let us see whether this constitutes a group of infinite order. Infinite order means there is no limitation on the number of elements of the group. Here the identity element is 0 and mode of combination is addition. You add 0 to any elements, it will not change the element. Now, even if you combine 2 elements, say minus 3 and plus 3, combination will get 0. So, here minus 3 and plus 3, they are inverse to each other. So, like this you can verify, even you can go for the law of associative. You take minus 3 plus minus 2 plus minus 1, net result is minus 6, and minus 6 is an element of the group. Now, you combine in another way, minus 3 plus minus 2 within bracket, then plus minus 1, again the same result. So, here you can combine or associate the element in any way, you will get the same result. So, and the inverse, as I have already pointed, inverse of integer n is n inverse, and for here it will be minus n, inverse is plus n. Now, for example, which I have just taken over here, law of associative by taking minus 2, minus 1 and minus 4, we have verified. You try any combination, any operation, you will get this element belonging to the group. You can take any number because it is an infinite order group. So, all negative integers and all positive integers with 0 as the identity and mode of combination as addition constitutes a group. Now, let us take another example, that is, show that the group -1 and 1 under the mode of multiplication constitutes a group. That is, here I am having two elements and I have to just find out whether it is a group or not. Group means these two elements which are there, -1 and 1, they should satisfy all the four conditions. First, let us find the identity element into the group. There are three possibilities. -1 is the inverse, +1 is the inverse, or there is no inverse. Let us take the following products. 1 into 1 is 1, -1 into 1 is -1, -1 into -1 is 1. It means number 1 does not change. Number 1 does not change 1. -1, when these are combined, they change the number. So, here identity is 1, not -1. And if we take the mode of multiplication as the combination mode, then we can verify all the four properties. That is, 1 is the identity. You multiply with any of the number, multiply with 1 or multiply with -1, it will not change the identity. So, I is the identity element, and rest of the properties you can easily verify, that is, whether all the four properties are verified or not. Let us take another example. We take the powers of, say, 2, 2 raised to the power -1, 2 raised to the power -2, 2 raised to the power 3 raised to the power -2, so on the negative side, and 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2 on the positive side is an infinite group under the mode of combination as multiplication. Let us first find the identity by taking the following products: 2 inverse 2 into 2 raised to the power 0, then 2 inverse 2, 2 inverse 1 is equal to 2 inverse 1. That is, if I take 2 inverse 2 and combine with 2 inverse 0, I will get the result 2 inverse 2. So, like this, you take any element combined, or that is multiply with 2 raised to the power 0, you will get the same result. That is, 2 raised to the power 0 is an identity. And like this, we can verify the law of associative also and inverses also. This you can try in yourself. Now, I will just give or explain the properties of a group in a systematic manner by taking very simple example, that is the phase movement of a soldier in exercise drill. For this, we will take a soldier and we will define his phase movement. Now, let us take the example of the phase movement of a soldier. Left turn stands for left turn, R stands for right turn, and A stands for about turn, and E means stand still, that is, do not do anything on this molecule. So, I will make use of these four movements, and I will just show you that these four movements constitute a group. Here I am saying movement. These are not the symmetry operation on soldier. These are the phase movement. These four phase movement L, R, A and E of soldier constitutes a group with E stands at ease as identity, mode of combination as one phase movement on command, followed by another phase movement combined. These four phase movement on command constitute a group. Let us now verify the four properties of the group. According to the property 1, there must be an element into the group which on combination with other element does not change the element. Now in this soldier example, this is E, that is no command or stand still. This is the command. It means I am doing nothing. Now if I give the command A, about turn, and then I say E, it means it will remain as E. So here A followed by E is A, that is E is not changing this molecule again. Now that is the soldier follows the phase movement in order, as standard is followed by about turn by 180 degree. The combined operation, the combined movement is equivalent to A. That is also E into A, E movement followed by A movement is equal to A. Similarly, if I take L operation, that is like this, followed by E operation or E movement, I will get the net result as L. Now if I take right movement followed by E, E is again not doing, I will getting R. So here I am having 4 elements into the group, E, L, R and A. So here the group is of order 4. Now you carry out any operation on this molecule. Now let us say the combination of 2 elements is another element of the group. Let us say this property. Now for this, let us take LR is equal to E. Let us try to see. Now if I write down LR is equal to E. Now in this way, what I have to do, I have to perform this symmetry operation starting from the right hand side. That is, you first perform R, that is this operation. Then I ask you left turn means again this. What is the net result? Is E. Now let us take AR product. AR means R operation first followed by this. Now if I take R operation, it is like this. Then I say about turn is again like this, 180 degree. The net result is left turn. Now I take the product A, that is I take the phase movement followed by phase movement A. This is first phase movement and this is now the second phase movement. I will get the result E. So like this I can verify all the properties of the group. Now let me take the result LAR, that is operation R followed by A followed by L. What is this result? Now I perform right operation, R is written, so I just go for this. Then after this A operation, A means about 180 degree rotation, that is I am giving this 180 degree rotation. Then left turn, this is my left turn, I gave this. This is nothing but if you see the original, it is about turn. So like this you can verify all the 4 properties, and this is very, very simple. You can introduce this group properties by just taking this example of soldier and just telling the students that it is very easy to explain. Now like this you can verify all other properties of the group in this manner.
To find total symmetry elements in it and total symmetry operations generated by these symmetry elements, we take an example of water molecule. The above figure shows the various symmetry elements in the structure of water molecule. Symmetry elements in H2O molecule are E, C2, sigma xz, and sigma yz. Thus, we can say that total symmetry operations generated here are sigma xz, sigma yz, C2 and E in H2O. That is, only 4 symmetry operations are generated by 4 symmetry elements. In case of H2O molecule, number of symmetry elements and symmetry operations are same. This is not always the case. These 4 symmetry operations constitute a group, that is, sigma xz, sigma yz, C2 and E is a group of order 4. Number of elements in a group is its order. It is the symmetry operations that constitute a group and not the symmetry elements. Here, E is the identity. First property says that group element remains unchanged. The above figure shows all these results. Symmetry operations are always carried out from right to left. The second group property says that every element has its reciprocal. Symmetry operation and its reciprocal, when combined, give identity. In the figure above, we notice that the symmetry product C2 dot C2 is equal to E. It means C2 is its own inverse, that is, C2 inverse is equal to C2. Similarly, sigma xz is equal to E. Therefore, sigma xz is the inverse of itself, and similarly, inverse of sigma yz is sigma yz. Thus, in the group, each element has a unique inverse. Here, each and every group element, symmetry operation, is the inverse of itself. The third property is the law of associative multiplication. In the figure shown, these are associative products for water molecule. The fourth property says that product of two or more elements or square of the element must be an element of the group. The combinations of various symmetry operations are shown in the figure. These are some more products according to the fourth property. Thus, all the four properties of a group sigma xz, sigma yz, C2, E have been verified. By taking another example of C3 axis in an equilateral triangle, we see that operations generated by C3 axis constitute a group. C3 axis generates the following symmetry operations: C31, C32, C33 is equal to E. That is, all three symmetry operations are generated. Various symmetry products are shown in the figure. In continuation, these are the symmetry products which can easily verify all the four properties discussed earlier. It is the symmetry operations that constitute a group and not the symmetry elements. Subgroups can be defined as a part of the main group which satisfies all the properties of the group. That is, within the main group of order H, there may be smaller groups of lower order than H. 1. Subgroup always contains identity element E. 2. E itself constitutes a group of order 1 and it is trivial. 3. The subgroup of order 2 also contains identity element E. 4. Groups of order 2 can be E, A, E, B, E, C, etc. in the main group A, B, C, E. 5. Subgroups always follow the group conditions of the main group. 6. Order of the subgroup is an integral factor of the order of the main group. 7. If the order of subgroup is G, then H by G is an integer and not in fraction. Our first step is to find subgroups. In this, E is trivial group of order 1 and non-trivial subgroups of order of 2 can be E, A, E, L, E, R, L, R, A, L, A, R, and so on. Out of E, A, E, L, E, R subgroups which contain E, only E, A subgroup satisfies all the group conditions, and this is the only subgroup of order 2 of the main group LRAE. EA is equal to AE is equal to A. AA is equal to E, AAA is equal to A inverse is equal to A, and E inverse is E, and so on. The remaining subgroups of order 2, E, L, E, R, L, R, A, L, A, R, etc., do not constitute groups. By taking an example of water molecule, we can find the subgroup in the group sigma xz, sigma yz, C2, E. Here E is always a subgroup of order 1. The other subgroups of order 2 may be E, C2, E, sigma yz, E, sigma xz, sigma xz, sigma yz, C2, sigma yz, C2, sigma xz, and so on. Here, E, C2, E, sigma yz, and E, sigma xz are the subgroups of order 2, and sigma xz, sigma yz, C2, sigma yz, and C2, sigma xz are not the subgroups of order 2, as these do not have E as the member of the subgroup. To verify this, we need to see the products of symmetry operations in water molecule. The symmetry operation products sigma xz, sigma yz, C2, sigma yz, and C2, sigma xz are not the subgroups of order 2, as these do not have E as the member of the subgroup, which is a must. The products sigma xz dot sigma yz, C2 dot sigma yz, C2 dot sigma xz gives C2, sigma xz and sigma yz respectively, which are not the elements of the subgroup under consideration. In this figure, we can see some more combinations of C2 with C2, sigma xz with sigma xz, and sigma yz with sigma yz, which gives the resultant E. It is another way of subdividing a group into smaller collection of elements. Class can be defined as the collection of all conjugate elements of the group. It has different bases for the division of the group. All conjugate elements are related by similarity transformation. The order of a class is the integral factor of the order of the main group. For similarity transformation, if A and X are the element of the group, then X inverse AX operation will be equal to some element of the group, say it is B. This transformation is written as X inverse AX is equal to B. We can also express the result by saying that B is the similarity transformation of A by X, or we can say that A and B are conjugate elements of the group. The characteristics of conjugate elements are as follows. Every element is conjugating with itself, which means if we take element A, then it must be possible to find one element X in the group such that X inverse AX equals A. If A is conjugate to B, then B is conjugate to A, that is, A equals X inverse Bx, then there must be another element in the group, say Y, such that B equals Y inverse Ay holds good. If A is conjugate with B and C separately, then B and C are conjugate with each other, or if A is conjugate to B and B is conjugate to C, then A will be conjugate with C also. To find a class in a group, we need to take a finite group A, B, C, D, E, and F of order 6 with E as the identity element in this group. In this group, we take the similarity transformation of each and every element by all the elements of the group, including the element itself, and these are E inverse EE is equal to E, that is, the element itself. A inverse EA is equal to E. B inverse EB is equal to E. C inverse EC is equal to E. D inverse ED is equal to E. F inverse EF is equal to E. That is, E transforms into itself by all these transformations. Therefore, E constitutes a separate class by itself, and number of elements in this class equals to 1. That is, order is 1. And similarly, one can work out other similarity transformations for A, B, C, D, E, and F group. Now take element A and perform similar transformations on it. The results are, say, A inverse AE equals A, B inverse AB equals C, C inverse AC equal to B, D inverse AD equals B, F inverse AF equals C, A inverse AA equals A. In all these transformations, A is transformed into A, B, C only. Thus, A, B, C constitute a class of order 3. These are the similarity transformations in pH3 molecule, as E is the reciprocal of E and reciprocal of C31 is C32. This is the third similarity transformation in pH3 molecule, where C31 and C32 are the reciprocal of each other. This is the third similarity transformation in pH3 molecule. This is the fourth similarity transformation in pH3 molecule, as sigma V dash inverse is equal to sigma V dash. This is the fifth similarity transformation in pH3 molecule, as sigma V inverse equals sigma V. This is the sixth similarity transformation in pH3 molecule. Thus, we can clearly see that all the similarity transformations on sigma V by E, C31, C32, sigma V, sigma V dash, sigma V double dash give results as sigma V dash, sigma V double dash only. Similarly, by carrying out similarity transformation on sigma V dash, sigma V double dash by E, C31, C32, sigma V dash, sigma V double dash give the results as sigma V dash, sigma V double dash only. Thus, out of 6 operations of pH3, sigma V, sigma V dash, sigma V double dash constitute a separate class. Thus, in a group, C31, C32, sigma V dash, sigma V double dash, there are 3 classes: 1. E of order 1, 2. Sigma V, sigma V dash, sigma V double dash of order 3, and 3. C31, C32, E of order 3. These are some simple rules for finding classes. The simplest way of arranging the symmetry operations into classes is to arrange them into sets of equivalent symmetry operations which have equivalent effects on the molecule.
Now, in this module, we have learned about the importance of group theory and historical development mentioned in very brief. Definition of a group is given and explained. Group postulates are stated and explained. Group postulates are verified by taking various common examples. Example of phase movement of soldier has been explained in detail with the help of diagrams of a soldier. Theorem of reciprocal stated and duly verified. Definition of some more common type of groups: abelian group, cyclic group, finite and infinite groups have been introduced. Total symmetry elements present in the given molecule explained. Total symmetry operation generated by all symmetry elements. Total symmetry operation generated constitute a group has been explained in detail. Symmetry operation generated by C3 axis of an equilateral triangle also constitute a group. It is the symmetry operation that constitute a group, not the symmetry elements. Further, various types of subgroups into the main groups were also discussed, and subgroups were found into the main group. Also, the idea about classes is introduced, conjugate elements were discussed, and some common points were also mentioned how to find classes into a group without performing similarity transformations.